let's prove another trigonometric identity. This one is a little bit harder, but let's keep practicing those steps that we talked about in the last video. And actually, we only got to step 1, and I didn't talk about step 2 and 3, but we've already kind of talked about those. But let's return back to the guidelines. Step 1 was to start with one side, choose the more complicated side. Step 2 says use known identities. Basically, use algebra and the identities you know to change the side you started with, bring fractional expressions to a common denominator, factor, and use fundamental identities to simplify. So what it's sort of saying to do is use algebra. Like in the last video, we used the distributive property, we used cancellation, we used basic algebraic principles to simplify. And we also used known identities like the reciprocal identity and the Pythagorean identity to relate this starting expression into something simpler. And that's that's all we did. I just forgot to kind of summarize. But another thing, another recommendation that I thought is quite helpful sometimes in this example specifically is bring fractional expressions to a common denominator. So let's say, for example, I have fractions. In order to add them, we need to have a same denominator. So that's another thing that can help us progress is to use the LCD. And sometimes even factoring or using other algebraic tricks can help progress through these types of problems. And step 3, this is something else I mentioned before, but converting to sines and cosines. If you're stuck, try to change everything to sines and cosines. Like that was step 1 in the previous example, right? I changed secant to terms of cosine. And all of those 3 steps are quite helpful. So let's start with this. Let's do a new example of keeping those 3 tips in mind. But tip number 1 is start with the more complex side. So looking at this identity, I would definitely say the right-hand side is more complicated because it involves fractions, it involves a bunch of crud. The left-hand side is also I wouldn't exactly say it's simple, involving secant and tangent. But what I would think about is, can I see a possible way of changing this into this? Like, I don't know, tangent is sine over cosine, secant is 1 over cosine. Technically I can see a way that will work, but it seems way more difficult to change this side and this. And over here, well, technically, it might not necessarily be obvious what do I do first because these are very weird expressions as well. But let's go ahead and take the right-hand side. Basically, it's like whatever side has more stuff in it, that's where I would begin. So let's just go ahead and copy it down again. And again, my goal is to not work on both sides of the equation, but start with one side and show that it's equal to the other side using a series of irrefutable steps. And notice that in number 2, it said that bring fractional expressions to a common denominator. And that's exactly what I could do here, because what I can see is I have this fraction minus this fraction. You might be tempted to say, okay, well, I could cancel these things. But remember, with fractions, the rules don't change just because we're dealing with trig. It's still the same basic mathematical rules. In order to add or subtract fractions, I need to have a common denominator. And in this case, the denominators are not the same. And what I could do to match the denominators is multiply them by the opposite thing. So it's kind of like if I have 1/4 minus 1/3, the way that I could do this is I need to multiply by the opposing denominator, right? And once I have a common denominator, 12, I can multiply. But so like in this case, I could multiply the first one by 1 plus sign and this one by 1 minus sign. And that would make sure that those denominators are equivalent. But that's not all, right? Because in order to make sure that my fractions are equal, I need to do the same thing to the top that it did to the bottom. Because if I'm trying to do 1/4 minus 1/3, I can't just multiply by 3 and 4 on the bottom. That will change my answers. But if I use the equivalent fraction principle, I multiply the top and bottom by the same thing. It's really multiplying by 1. I'm not changing its value. And so really, we're using a bunch of fraction rules here to progress algebraically, through this problem. But so, I also need to do the same thing to the top. 1 plus sine A on that one, and 1 minus sine A on the second fraction. And that way, I'm not really changing the values of each of those expressions. And well, what that would give me on the top of this one, we'll have 1 plus sine A times 1 is 1 plus sine A, and the denominator would be, well, 1 plus sine A times 1 minus sine A. And what you might notice is that coincident or not so coincidentally, these actually form a difference because I have 1 plus something and 1 minus the same thing. And if I FOIL that out, well, that's going to give me 1 minus sine A plus sine A. So the minus sine A will cancel with the plus sine A, and then minus sine squared. So really I'm left with 1 minus sine squared, a difference of squares. It's like x plus y and x minus y. It's the same two things, 1 plus, 1 minus. Always has a simple result. And then in the second fraction, I have, well, 1 minus sine times 1 is 1 minus sine. And on the bottom, I have the same denominator. That was the initial point, right, is to make the same thing on top and bottom, 1 minus sine squared A. You might be tempted to cancel the signs here, but remember that cancellation property does not apply here because these are not factored. Remember, in order to cancel, there can't be adding and subtracting within a fraction. So be careful with your algebra, because in these problems, I've seen a lot of time, a lot of students make a lot of mistakes with the fundamental algebra, and that's one thing that you need to be very careful with. But anyways, now since we have a common denominator, what we can do is go ahead and add across the top, because now that this is the same, what I would get is, well, this numerator minus this numerator, right? And the denominator will stay the same as rules of fractions. So now we have a common denominator I can add across the top. So I'd have this numerator minus this numerator. So what I'd have is 1 minus 1, which is of course 0. And then I have sine A minus a negative sine A. Remember that the negative here will distribute to both terms, because when you subtract a fraction, you're subtracting the whole numerator. And then subtracting a negative sign would give me positive sign. So really, I have sine A plus sine A, which is 2 sine A. And that gets me a little closer to where I'm trying to get. Also, remember that the goal is to get this whole horrible thing into this whole horrible thing. And notice that notice I'm getting a little closer, because first of all, in making a common denominator, I'm joining them together as a single thing, because here I started with 2 fractions, here I only have like 1 term. So that's kind of progress. And now I have this 2, which was in the left-hand side. So I can, at this point, I'm kind of like analyzing my situation. This is looking good, right? I'm getting closer to the desired goal. I'm not there yet, but I can see some progress. And another thing that I could recognize is, well, I have 1 minus sine squared on the bottom. And kind of like in the last question, whenever you see sine squared or cosine squared, especially with each other or with 1, those often will change using the Pythagorean identity, because 1 minus sine squared is equal to cosine squared by the alternate Pythagorean identity, for the same reason we said before. And so I can kind of change that square 1 minus sine squared into a cosine squared. And again, it's kind of cleaning things up, making things better and better. And now that I'm kind of getting close, notice that I actually have a sine over a cosine and another cosine, but over here I have a tangent. Well, tangent is sine over cosine, so I can kind of think about this in parts. Well, I really have 2 times sine A over cosine A, because that's what cosine squared means, right? It's just something times itself. And at the end of the day, I'm actually pretty much done now, because this all makes tangent, right? And what I could think of is, well, what I have remaining is 1 divided by cosine. 1 divided by cosine is secant. So looking back at my initial goal, I have 2 times tangent times secant. Well, that's exactly what I have here. So let's go ahead and hash that out, and we are almost done with this one. But basically, I could rewrite this in a way where we'll have 2 times the fraction sine A over cosine A. But these are steps where you could skip these individual steps and just kind of say, okay, well, that's 2 times tangent times secant. You wouldn't necessarily have to write all this out. But these are all properties of fractions, basically, that if I have, I can break that fraction up into pieces. And again, this would be, well, just, 2 times this, and all of these would multiply on top, and this would just leave me with 2 sine A over cosine squared, which is equal to what I had over here. And ultimately, this is equal to 2 times the tangent of A times the secant of A. And I am now done because I have shown, starting with the right-hand side, that that makes the left-hand side proof. And notice I didn't actually show my steps here, but in explaining it, hopefully it was kind of apparent what I was doing, right? Step 1, match the denominator. Step 2, use property of rational expressions, add or subtract across the top. Step 3, apply Pythagorean identity. Step 4, split up the cosine. Step 5, split everything up. Step 6, done. Convert from sines and cosines back into their individual reciprocal functions via reciprocal identities. And again, you don't have to write out your steps, but if you do, that's awesome. That's like is the best possible thing you could do, like I did up here. Actually say, what did I do? I didn't really leave us enough room in the packet here to do that. So that's fine. And I think that's enough identities for right now. One other thing you can do before I wrap this video up is you can actually work on both sides separately. So this one is quite challenging too. I'll leave this for you as a challenge if you want, and if you get stuck, please drop by Zoom or email me and I can give you some hints. But another thing you can also do is technically you could start with one side and simplify this side, and then work on the other side, simplify that side. And as long as you get those two simplified answers to be the same, that's an alternative way of proving it. So technically, you don't just have to work on one side. You can work on both sides separately, simplify them, and if you can show that they both simplify to the same thing, logically that also makes sense, right? Because I can show that each of those two sides are equal in that way. So it's an alternate strategy, also totally fine. And on the next page of your packet, there's a bunch more, starting with a few fairly easy ones and moving to some more complicated ones. And another thing, for those of you who stuck around and have actually watched the whole video, I'm going to put exactly one of these 5 on the final verbatim. So there's a little incentive for you to actually try the ones in the packet, see if you can figure them out. And for me, these are all kind of like puzzles, like, right? It's something that I know must be true, and I want to figure out why. I want to, piece it together using all these other puzzle pieces. And to me, it's quite enjoyable sometimes. Obviously, if we get stuck, it's frustrating, but just remember, it takes practice. And each one that you do figure out, think of it as a step towards practicing and figuring out more and more complicated ones. And I was not always as good as I am at these today. Today I could take just about any one and I'm pretty confident I could figure it out. Like literally, you could probably give me just about any identity you could find. But I did not used to be that way. When I first started teaching trig, it took me a bit of time to learn how to be this good. And so that's what I'm saying is, if you're getting stuck, that's very normal. That's fine. I'm not going to give you a million hard ones on the final, but I want you to have the basic idea down. So practice some of these and use these as a little studying board for the final. And so we're almost done for this week's lecture. In the next video, I wanted to talk about some new identities and get into the geometric reasoning behind these and kind of discuss some alternative identities and why they're useful. And we'll go ahead and try to wrap up lecture for this week before it gets too long. Because while I did have all of identities in one day, this is absurd. This is probably at least 2 or 3 days worth of lecture, and I don't want to overload you guys with too much all at once. So I think that's enough for this week. I'll be working on some more videos on 4.6, 4.7, and 4.9, as well as some calc prep for the final. Anyways, hope you all are well. As always, let me know if you need anything. Email me, come to Zoom. Always nice to talk to you guys and check in where you're at. Because from a lot of you guys, I haven't really heard from you, and I just hope you're well. And you don't have to necessarily fill me in. And I'll take it as no news is good news. But for those of you who do drop by, it's nice to get a little bit of sense of community and, I know a lot of you guys in this class have been a little bit quiet, which is totally fine. Just want to make sure you know that I'm available and I do care, and I'm here to help. So anyways, see you all next week.